Hey, welcome to The Explainer. Today, we're going to pull back the curtain on a secret weapon scientists use to cut through all the confusion out there. It's a tool that helps us find the truth when it feels like every new study is saying something different. And trust me, once you get it, you'll never look at those crazy headlines the same way again.
You've been there, right? We've all been there. You read a headline that says one thing, and the very next week, you read the complete opposite. It's so frustrating, and it makes you wonder, what am I even supposed to believe anymore?
So one day you see a study that makes you think, awesome, I'll have another cup.
And then boom, the next day you see this. And suddenly your simple morning habit feels, well, a lot more complicated. So how do we find the real story when all the evidence seems to be fighting with itself? Well, believe it or not, there is a way. It's called a meta-analysis, and the best way to think of it is as a study of studies. Seriously, instead of getting hung up on one little piece of the puzzle, a meta-analysis gathers all the relevant research on a topic, mashes their data together, and looks for the bigger picture, the overall trend. It's how we find the signal in all that noise. Okay, let's really dive into this. To see how it works, we're going to look at a real-world meta-analysis. This one's about the effect of bicarbonate on gum health. And the central piece of evidence we're going to look at is a cool little graphic called a forest plot. Okay, I know, at first glance, this thing might look a little intimidating, maybe like a bunch of scientific hieroglyphics. But I promise you, it's not. It's actually a visual story of all the evidence, and each one of these lines is like its own little chapter. So let's just start with one line. See that little square? That tells you the result of that one specific study. Simple enough? Now that horizontal line running through it, that's the confidence interval, which is basically just the margin of error. And hey, notice how some squares are bigger than others? That's on purpose. Bigger studies, the ones with more people in them, they get more weight in the final analysis. They're more influential. Now, look at that solid vertical line right down the middle. That's our line of no effect. If a study's square and its little margin of error line fall to the left, it means the result favors the treatment, in this case, bicarbonate. If it falls to the right, it favors the control group. And if that horizontal line happens to cross over the middle bar, it means the result isn't statistically significant. So after you look at all those individual studies, all those squares and lines, your eyes should go right to the diamond at the bottom. This right here is the grand finale. It's the pooled estimate. It's the single combined result of every single study in the plot. This is the signal we've been looking for. But hang on, if you look closely at all those individual studies, you'll see they don't all tell the same story. And this is where the real magic of a meta-analysis comes in. It's not just about averaging results. It's about making sense of the disagreement. Let's just zoom in on the studies that lasted 6 months. The aquagragium study found a small effect, minus 0.20. But then the JOST study found a much bigger effect, minus 0.62. And then look at the Yankel study. It found almost no effect at all. So yeah, they clearly don't agree. Now, the meta-analysis doesn't just eyeball this, it actually gives us a number to quantify this disagreement. And for this group of studies, that number is a whopping 95%. So what does a 95% disagreement actually mean? Well, it's not just random noise. It's a measure of something called heterogeneity. It's a fancy word, often shown as I-squared, but the concept is pretty simple. It tells us how much of the variation we're seeing is because of genuine differences between the studies. Like maybe they use different populations or different methods versus just plain old random chance. And 95%, that is extremely high. It's a huge red flag that our studies aren't just a little different, they are telling fundamentally different stories. So when you have that much disagreement, you can't just take a simple average of the results. That would be totally misleading. You need to use a statistical model that actually accounts for the fact that the real world is messy, and the true effect might not be one single number. This brings us to 2 different ways of thinking about the data. A fixed effect model is kind of like assuming there's only one true bullseye, and every study is just a slightly off-target attempt to hit it. But a random effects model, it's much more realistic. It assumes that because of all those real-world differences, there might be slightly different bullseyes for each study. And with 95% disagreement, we know we're not aiming at a single target. So the random effects model is definitely the way to go. Now, here's the really cool part. We don't just have to accept this disagreement and throw our hands up. A meta-analysis actually lets us play detective. We can investigate why these studies might be giving us such different results. So one obvious question here is, could the length of the study be the culprit?
Maybe the effect is just different for studies that only followed people for 3 months compared to those that went on for 6 months. We can actually test that.
So, the analysis splits the studies into two groups. We can see the combined result for the 3-month studies is minus 0.17. For the 6-month studies, it's minus 0.24. Okay, so they look a little different, but are they statistically different?
And the answer is no. The test for these subgroup differences shows that this variation is likely just due to chance. So our detective work tells us that the length of the study isn't the smoking gun here. The real reason for all that disagreement might be something else entirely, maybe differences in the patients or the products they used. The mystery continues. Okay, so where does all of this leave us? We've waded through a bunch of conflicting results, we've put a number on their disagreement, we've used the right kind of statistical model, and we even investigated some potential reasons for the conflict. We've gone from noise to signal. And here it is, the overall diamond for all the studies combined. This is our bottom line. After accounting for all that variation and disagreement, the analysis finds a statistically significant effect. And we know that because the confidence interval, that range from minus 0.28 to minus 0.12, is entirely to the left of that no effect line. We can be confident that overall, the evidence shows bicarbonate really does have a positive effect on gum health.
So let's just recap the big stuff. A meta-analysis gives us a much more reliable answer because it's pooling all the evidence together. That forest plot is the key visual that tells the whole story at a glance. Remember that word heterogeneity? It's just a measure of disagreement, and a good meta-analysis doesn't ignore it. It embraces it to find a conclusion that's truly robust. So, the next time you see those conflicting headlines, you'll know not to take any single one as the final word. You now have the lens to look for the bigger picture, to look for the meta-analysis, to find the diamond, and to ask the most important question of all: what does the entire body of evidence actually say?